Okay, so this is going to be me going through the 2025 Unit 2 paper, both the stats and the mechanics part. Okay, so as usual, we've got to make sure that we show all of our workings so we can pick up any method marks just in case we make any mistakes. So on to question number 1. The giveaway when you're reading this one is where it says this average rate of 1 every 10 minutes. So you should be thinking by this point, well, when you see that kind of phrase, you should be thinking of the Poisson distribution. So we know straight away that if we define our variable, let x equal the number of transactions, and then it's in an hour, 1 hour. Oops. And so we can say something about the distribution of x. We know it's Poisson, but what's slightly different here is in the question it talks to us about an average rate of 1 every 10 minutes, and then we're looking at an hour period. So 1 every 10 minutes would mean that we'd expect on average 6 per hour. Then looking at the actual question part, find the probability there will be exactly 5 transactions. So we're looking for the probability that x is equal to 5 in this one, okay? And you're going to have to show your working out for this, so don't just put your answer straight into your calculator and leave it at that. So you want to do lambda to the power of x multiplied by e to the power of minus lambda over x factorial. Okay, then at that point you can put it into your calculator and you should come out, and just a reminder for stats, we're going to be giving our answers to 4 decimal places, so 0.1606. Okay, now there are other ways to do this. If you'd like to use the function on your calculator, I'll do it over here. Probability of x is equal to 5 is also the probability of x being less than or equal to 5 minus the probability of x being less than or equal to 4. So you could work out that calculation. It just involves a lot more calculator clicks, so I'd prefer to do it this way. Okay, moving on to the next part. During a busy period, the average rate is 10 transactions per hour. The cost per transaction is 30. Okay, so we're saying then that if y is the number of transactions per hour, we're saying that y is Poisson with an expectation of 10, or a parameter of 10. Each transaction is £30. Looking at the question then, at least 360. Well, that means, so $360 means 12 transactions. Okay, because 360 divided by 30 gives us that 12. So that means in this question, we're looking at what the probability is that y is greater than or equal to 12. Yeah, I suppose you could say that y is the expected amount of money per hour. Yeah, I suppose you could do it that way, but I prefer this way. And so you can't do that directly on your calculator unless you've got one of those fancy graphical calculators. So we need to think that if we want 12 or more, that's everything except what's less than or equal to 11. So 1 minus the probability of y being less than or equal to 11. Okay, or you may want to think of it to begin with, I suppose, as 1 minus the probability of, oops, that should be a y, less than 12. Maybe that's an easy way to think of it first. And then you can put the second bit into your calculator. So we're going to do 1 minus, work out that probability, 0.6968, I think, yeah. And then we're going to do that subtraction, so 0.3032. And there's our first 6 marks. Lovely, moving on. Okay, so if we have a look at this question, we're given a probability distribution. We don't need any context for this, just a bunch of numbers in a table. Whatever x is, it can take values 2, 3, 4, or 5, or whatever that outcome is. It can take values 2, 3, 4, and 5, and those are the probabilities. It's really important here to note that observations are independent from one another, so we suspect that there's going to be some multiplying probabilities going on here. So whatever this experiment is, we're doing it twice, and the outcomes of those are x1 and x2. Find the probability that x1 plus x2 is equal to 6. So the start of this question is really thinking, well, how can I make 6 using 2, 3, 4, and 5, and add in 2 scores together? Well, I can get a 2 and a 4. Okay, so I can get a 2 and a 4. I could also get a 3 and then another 3. Okay, I'll put them in brackets so they're clear. Don't mix those up for coordinates. And then the final option is a 4 first and a 2 second. So they're actually the same event. So a 4 and a 2. Okay, so let's think how we're going to work out the probability. So the probability of x1 plus x2 being equal to 6 is going to be, well, to get a 2 first, that happens that proportion of the time. Then to follow that up with a 4 is that. And you'll notice that a 4 and a 2 is just the other way around, so the probability doesn't change. So I'm just going to go ahead and double that straight away. Or, so that is this one and this one taken care of. Or I could have a 3 and a 3. The probability of getting the first 3 is 0.4. The probability of then getting another 3 is again 0.4. So that first term there is 0.06. The second term is 0.16. So we get an answer of 0.22. Okay, that's a really nice 4 marker there. Moving on. Okay, so looking at this question, Martin's designing a new question for a multiple choice question quiz. It's got 3 options. That's the wrong pen. It's got 3 options, one of which is correct. And then it gets odd, difficult to answer correctly. He claims that people will do better if they select their answers at random rather than trying to work it out. I don't understand what that means, but I guess you don't have to for this. So this looks like the start of a hypothesis testing question, and we're going to consider the probability of somebody getting a question right. So we'll start with the null hypothesis and then the alternative hypothesis. Now you can write these as sentences if you want, but it's much quicker and easier, in my opinion, to write them as letters and numbers and statements with probabilities in. So the probability that somebody gets a question right, if there's a question with 3 options and they guess it, well, that's going to be 1/3. Okay, he's designing this these questions so that the probability of trying to work out the answer means you're less likely to get it right. So there'll be a probability of less than 1/3 that somebody gets it right by trying to work it out. Okay, then we're into the main part of the hypothesis testing question. So for dotty number 1, we need to define our random variable. So let's say let x equal the number of people who got the question correct, number of people getting the question correct. New question correct. Now, we're always going to assume until we prove otherwise that H0 is correct, and under H0, that means we've got a binomial distribution, and let's have a look at what the parameters of that distribution are. Well, we've got the 1/3 probability from up here, and then we've got 63 trials. Okay, so we can say under H0, or if H0 is correct, we can say that X is binomial, 63 trials, and a 1/3 probability of getting each one correct. And the number that I like to consider here is called the expectation. So if you get a third of questions right, you do 63 trials, you'd expect 21 correct answers, the expectation. And that's just important to see which tail we're going to end up testing. Okay. He finds that 15 people answer the new questions and 48 people answer incorrectly. So we want to find out what's the probability of something more extreme than 15 people answering the new question correctly. And if you think of your binomial distribution, that's absolutely terrible, but I've got my 21 there at the centre, my 15 is here. Now I know I've drawn a bell curve there, but imagine there were bars in that kind of shape. And so more extreme than that 15, which is the value given in the question, is going to be less than 15. So the p-value is the same as the probability of X being less than or equal to 15. So as extreme or more extreme than the observed value. And we can put that into our calculator. We can use the stats tables. Okay, and we come out with 0.0679. Okay, so there is our p-value. Okay, and that's what it asks for in dot E1. I'm guessing then, yeah, we're going to complete the hypothesis test. So if we have a look then, so we've got a 5% significance level, and people roll their eyes when I say this, but if P is low, H0 has got to go. And so what that's referring to is if your p-value is a small number, as in less than your significance level, that's when you can reject H0. But in this case, we would say since the p-value 0.0679 is greater than the significance level, and in case I didn't talk about it earlier, the significance level is this 5% up here. So since that's greater than 0.05, which is 5%, there is insufficient evidence. There is insufficient evidence to reject H0. Okay, so we've now got 4 out of the 5 marks for this part. You must answer in the context of the question. Okay, so you could say something as simple in this case as there's insufficient evidence to support Martin's claim, and that's probably what I would write in an exam because it's quicker. But if we think about the context of the question, Martin is saying that people are better off guessing than trying to work it out. Our hypothesis test does not show that that is true. And so that's what I'm going to write here. There is insufficient evidence. That statement, by the way, insufficient evidence or sufficient evidence, is something that absolutely must appear in your answer at least once. As you can see, I like to use it twice here as a belt and braces kind of approach, but it must appear at least once, otherwise you're not going to get these marks. Insufficient evidence, and you can include at the 5% significance level, but I'm not going to suggest people do better. No, in fact, I'm going to phrase it the other way around. Do worse by trying to work out the answer. When compared with randomly guessing. That's part of my issue with this question. I don't understand what that means, but I guess we don't need to really understand the context to get on with answering the question. Okay, there we are, moving on. Okay, and then on to the part C. We had a little bit of extra room on the next page if we needed to, but we didn't. Now suppose that Martin's question is such that the true probability is 0.2. Okay, calculate the probability of a type 2 error in that sample size. Okay, so a lot of the time when you see these probability of a type 2 error, it comes from a previous part where you actually have rejected your null hypothesis, and so you've got something like the critical region. Now that's not the case here, so the first thing we're going to have to work out is what the critical region is, so that we can find out, we can use that then with the actual probability that they give us. So that 0.2 is not particularly important just yet, but we're going to remind ourselves that x, my pen has gone a bit thicker there. So if you remember from before, x is binomial 63 1/3. Now you can do this however you want. I'm going to use my calculator, but I found that the critical value was when x was equal to 14, since the probability of x being less than or equal to 14, this is the first time it dips below that 5%. Okay, so that number there is the one that's important to me. Okay, now just to remind you, the probability of a type 2 error is the probability that something is in the acceptance region under the new distribution, okay, or under the given distribution. So if we know that the critical region is x is less than or equal to 14, that means if x is in that region, we would reject h0, but for a type 2 error to have occurred, we need to have accepted h0. So what I want is the probability of type 2 is then going to be the probability of x being within the acceptance region, which is greater than or equal to 15, under the now correct distribution of x being binomial 63 trials, but with this 0.2. So if you think, then that's the only thing really that's changed from what we had up here. We now know that this is the probability of them getting their question right. Okay, so we can work out that probability by doing, I'm going to stop writing this bit now. So I'm going to have 1 minus the probability of x being less than or equal to 14. Okay, under the new distribution. So notice that this bit here and this bit here are the same, but the numbers will come out different because we're using different parameters. And so that comes out then, if you work that out as 1 minus 0.7318, my calculator says, and then 0.2682. If you do the subtraction, interpret my answer in context. So that number there is 26.8%, so approximately 27%. So that means there's about 27% chance that Martin will come to the wrong conclusion if P is 0.2. What else could I say? Yeah, I think that would probably be my answer. If the probability that people answer the question correctly is 0.2, well then there's a nearly 27% chance that Martin's hypothesis test, or our hypothesis test that we're doing for Martin, leads to the incorrect conclusion. So if P equals 0.2, there is approximately 27% chance to come to the wrong conclusion. Okay, which I would say is quite high. Okay, moving on. Always nice to turn over the page and see a Venn diagrams question. Yeah, lovely. So we've got 4 events, A, B, C, and D. We can see that B is a subset of A, because B is wholly contained within A, and then we got some kind of overlap between C and D, and then A and B are mutually exclusive from C and D. So find the probability of A. There's a nice easy start. So A, purely A happening, so A without B happening, happens 0.17 of the time. So then we've also got to consider B happening. So the probability of A is everything in the A circle, which is 0.17 plus 0.13, which is 0.3. I think a lot of people would write the 0.17 here, but you've got to remember A is everything within the A circle, all the different bits, even if there's a subset, or particularly if there's a subset. Okay, next one then, probability of A happening and B happening. Okay, well, A and B happening together is just 0.13, just B happening, because B can't happen without A happening. Okay, so the probability of A and B is 0.13. Lovely. I'm guessing, looking at the diagram, that the next part of the question is going to be something to do with finding P and Q. So let's move on to the next question. Okay, then, as if by magic, my picture from over there, from the last page, has appeared here. Given that not C is 0.6 and the events C and D are independent, calculate P, Q, and R. I'll be honest, I didn't even see R in the picture last time. So we know that if the probability of not C is 0.6, this tells us that the probability of C is 0.6, so the probability of is 0.4, sorry. Probability of C is 0.4. We look at our Venn diagram, we can see that C is P plus 0.08, so that's 0.08 plus, I got it wrong again then, didn't I? I said P, I think I said C, but I meant P. So that tells us what P is. P is 0.32, so there's a nice easy start to this question. Then we know that since C and D are independent, I know that probability of C times probability of D equals the intersection, which is 0.08. So I can say that P plus 0.08, so that's the probability of C, multiplied by Q plus 0.08 is equal to 0.08. Now, you could do all of the multiplying out and everything, but if you want to be clever about it, well, think about what we just did, we know that that bit there is equal to 0.4. Okay, so in fact that's the more sensible way to do it. So you can say that Q plus 0.08 equals 0.08 over 0.4. Okay, or you can leave the 0.04 on the other side and expand the brackets. Okay, so this right hand side then is 0.2, which means Q is equal to 0.2 minus 0.08, which is 0.12. That's the second part of our question. And then the final one, given that Q is the bit outside of A and B and C and D, I would probably do 1 minus everything else to give me what R is. So I'm going to say that R equals 1 minus, well, the A and B circle is 0.3, the C circle is 0.4, and the bit outside of C but in D, which is Q, is 0.12, so that's 0.7, 0.8, so I think that's 0.18. Is our answer there? Lovely. Verify that on your calculator, obviously, but I'm pretty sure it's 0.18. Lovely. Nice question, that. I enjoyed that question. 8 marks in total, I think. I'm going to move on. Okay, lots of information in this table. WHO, we've the World Health Organization, and we've got life expectancy, and a bunch of other bits of data there. Give 2 ways in which this data could be cleaned. Okay, so there's a couple of things that hopefully jump out quite quickly at you. Number 1 to me is there's an empty box. Okay, so something's obviously gone wrong with whoever found this data. Either they just missed out Saudi Arabia, well, that's pretty much the only reason I can think of. They've just missed it out. So that's probably going to be one of my answers. Something else that looks a little bit fishy is this bit of data here, having an adult mortality rate of AB. Doesn't really make much sense either, so that could be one of my other comments. This entire column here, while there's nothing wrong with it, it feels odd to have duplicated data in my table, so I could probably cut that out as well. And then really the only other thing that might stand out is this number here, no, not that one, sorry, circling the wrong one. This one here, because it's significantly lower than all of the rest. Now that doesn't mean it's wrong, it doesn't mean there's been an error in calculating it or an error in finding this data, but it is significantly different. So I would be thinking, could it potentially be an outlier? May there have been some inaccuracy when this data was being collected? That would probably be my final reason, because there's nothing to make me suspect that there's anything wrong with that, but it is very different. So I think I'm probably going to go with the red one and the blue one. So I would say include the population for Saudi Arabia, and then Costa Rica adult mortality. Well, I either need to find it out or ignore the data. I don't really have any other options. Should be found or ignored. Okay, it doesn't really matter which. I mean, if we ignore it, then we can't really draw any conclusions about adult mortality. for these 6 countries because we've got a bit of missing data. Finding it, adding it in would be the ideal situation. Moving on. Okay, so we've got a scatter graph looking at life expectancy versus years of schooling, and they've given us the regression line, they've given us the equation of the regression line, but what I first of all look at here is the slope, or the direction it's going in, and it's got a positive gradient, which would imply to me some kind of positive correlation, not necessarily that there's any causation between these two variables, but there appears to be some kind of correlation. Part B, interpret the gradient of the regression line. So the gradient is this bit here, okay? And what that's telling you is that for each, it's not colouring in, for each 1 unit we move along the x-axis, which is years of schooling, there is an increase of 2.9527 on the vertical axis, which is the life expectancy. So that tells me that on average, for each additional or increase in the years of schooling, each 1 increase in the years of schooling, we might expect the life expectancy to go up by that number that I've highlighted in blue. Okay, some key words in it, and I will highlight all the important ones at the end. Okay, let's try and write in the correct pen. For each additional year of schooling, life expectancy increases by approximately 2.95 years on average. Okay, so it's really important that we are very clear what we are talking about. We are talking about an additional year of schooling, how it affects life expectancy, it increases it, and we must say on average, because you can see that these points, while they tend to follow a general trend, there are some that have more schooling but actually have a lower life expectancy. So if I draw your attention to this one and this one, for instance, the second one I highlighted has got over 16 years of schooling but has a lower life expectancy than the one with just under 13 years. So these are patterns, they're not rules that these two things have to follow. Okay, lovely. So that phrase on average, you must remember to put that in. That will lose you the mark if you don't put that in. You might get everything else perfectly, but that phrase on average must be there. Comment on the causal nature or otherwise of the correlation. Like with all answers in stats, you can say whatever you want. You can say there is causation between them. You can say there's not. You just have to back it up. Okay, so I'm going to suggest that there could be one is causing the other. There could be it's picking up. It's never done that before. There could be a cause. In general, and we are generalizing here, if you are more educated, you tend to make better, more sensible life choices. This could then lead to an increased life expectancy. More highly educated people tend to make better life choices increased life expectancy. You could even go a bit further and say, well, you could go the other direction and say they're not necessarily linked. There's some kind of third factor between them, and discuss a bit more about that. And I am generalizing here. It doesn't mean that if you go to university and get your PhD, you're gonna live really long because you make fantastic decisions. Not at all. But in general, the more educated you are, you might be making better life decisions and live longer as a result, possibly. Okay, moving on to part D, E, and F. Okay, let's get that question in there. Calculate an estimate for the life expectancy. So it's an estimate because we're using the equation of the regression line, and not every point of data fits on it perfectly, so it is just an estimate. So we're going to say that y for dot e1, y equals, and then we're going to use the equation from before, 2.9527 multiplied by the number of years of schooling, 14.6, and then we're going to add that 31.873, and that comes out at 74.98, so about 75 years. One thing that they do like to ask about in these questions, which they haven't done this time, is the significance of that y-intercept. And that's the one sometimes that actually doesn't make much sense in your context. But in this particular context, that would be the life expectancy for 0 years of schooling, which really I don't think makes much sense in this context, but that is what it would represent if it made sense. Okay, on to dotty 2. Comment on the reliability of my answer. Again, stats answer, you can say it's reliable, you can say it's not, as long as you're backing it up. Although in this one, I think it probably is reliable looking at the data, so I wouldn't be inclined to go towards unreliable, mainly because we're interpolating. If we were extrapolating, I would probably say it may be unreliable, but in this case, I'd say it's likely to be reliable, since interpolating also, if you go back and look at the graph, we do have a few points of data that are very, very close to 14.6, and their life expectancy is around that 75-year mark, which makes it feel even more reliable for me. Okay, then we've got even more information and lots of information here. So the entire data set was used to produce the following scatter diagrams. Years of schooling, life expectancy. So we can see we've got a similar sort of shape going on here. Generally, we've got a line of best fit or regression line that works. That looks pretty good, I'd say, for the data. However, I've got a bunch of things over here, which I suspect is what the next couple of questions might be about. But let's have a think. Let's move on. There we go. State the curious feature on the graph and what might be done about it. So we had a number of countries with 0 years of schooling. What I would suggest is that we could probably ignore this data. Yeah. So there are a number of countries with, can't spell with only has the one H, with 0 years of schooling. Now, I don't know any countries in the world where children don't go to school at all, and I certainly don't know many countries. So I'd say this is unlikely to be correct. Okay, what might be done about it? I would ignore that data in any subsequent analysis or calculations. I would ignore it. Ignore the data. Fine. Summary data below, so the sigma y squared, and n, as in the number of countries, show that the mean is that. Gotta love a nice show that question, because you know when you've done it right. And then what have we got? Claims that 71.6 represents average global life expectancy. Comment on this claim. Okay, so we know how to do the mean. Oh, I missed out. It says standard deviation as well. So the mean, given that they've used y, let's use y bar for the mean. That's going to be this sigma y over n. So 13105.9 divided by 183. Which is the 71.6 that we want. Standard deviation then. Okay, so let's find the variance first. So we're going to do sigma y squared over n. Where is it? Sigma y squared over n minus, and then it's going to be all of y bar squared. Okay, so I can say that therefore the standard deviation is going to be the square root of that. So let's start putting the numbers in. 950,615.47 over 183 minus the number that we just found, 71.6 squared. And we work that one out. And if you do all the typing into your calculator, you should get 8.1. Okay, so we've shown the thing that we want and we've worked that out. Now, yeah, we can't claim that because imagine we had two countries. So I'm going to make an obviously silly analogy here. Imagine we had two countries. In one country you had 100 million people, and in another country you had 100 people. In the big country, the life expectancy is 50. In the really small country, the life expectancy is 100. If you used this method to calculate the global life expectancy there, you'd come to 75, 50 plus 100 divided by 2 for the two countries, when obviously you've got far, far, far more people living live into a younger age, or fewer people live into an older age. So if we're going to do this, we need to do it a bit more sophisticatedly, and we should really be taking into account the populations of the countries. So we would need to do some kind of weighted average that takes into account the population size of each of the countries. So I'd say it may not be correct because we should use a weighted average which takes into account the size, the population of the country. Unlikely to be correct, as we should weight life expectancy based on the population of each country. Okay, hopefully my little analogy made sense. The bigger countries, they need to make up a bigger share of this mean. Okay, moving on. this is actually the end of the stat section, so we'll now go into the mechanics section. Okay, so into the mechanics question, nice start here with some vectors. So I've got two forces. Important to note here that this k is an unknown. If you're 13 doing this, you might know k as the third unit vector that we deal with, but don't get confused. Okay, we've only got two here. Given that the particle is in equilibrium, that's a super important word. Okay, and it's actually the first thing I'm going to deal with. Equilibrium means that vector g plus vector h is the zero vector. Okay, so I know that minus 4 plus k and oh no, I'm not reading the question, am I? That was silly. I know that it's in equilibrium under the action of the force 3g plus 2h. So 3g plus 2h equals the zero vector. So then that means 3 lots of g is minus 12 in the I direction, and 2k, that's 2 lots of h. And then I'm going to have 18 minus 18 from here, and that's going to be the vector 0, 0. So then we've got a nice little simple equation to solve. 2k minus 12 equals 0, k equals 6 as required. Nice straightforward 3 marks for us there. Okay, moving on. Okay, now we're going to do what I was trying to do before. So let's figure out the size of the resultant of g and h. So I've got minus 4 plus 6, which is 2, and then 6 plus minus 9, which is minus 3. So there is our resultant force. I can now say that the mass of the object, 0.5, times the acceleration vector is equal to this resultant force. Okay, and this is me using Newton's second law. And so when you divide by 0.5, that's the same as doubling. So I'm going to get 4 minus 6, because that's an acceleration, it's meters per second. Notice I've left my answer in vector form because it literally says vector there, but if it said determine the acceleration, that acceleration is a vector quantity, so I'd still need to know to leave it in this form. Okay, moving on. Okay, so using those equations, so we can do this with a simple bit of substitution. We don't even really need to go back to the graphs, but just because I like to, I'm going to show you where these two come from. So I've got just a generic velocity time graph here. So I've got v and t. Initial velocity is u, final velocity is v, and this time interval here is t. And so we can derive both of these. The second one comes from the area under that graph, and then the first one is the final speed is equal to the initial speed plus the gradient of this line times the time interval. Okay, so a times t actually tells us in this case what that height is there. Okay, you would probably derive that first one by finding an expression for the gradient of this line and then rearranging to make v the subject. But that's not actually what this question is asking. It's asking us to prove s equals ut plus half at squared. So the way I would do it is I would substitute the first equation into the second equation. So half of u plus at times t. Okay, so then I'm going to bring the t out the front. So I've got t over 2 times 2u plus a t, and then I distribute the t over 2. Now for the first term, t over 2 times 2u is just going to give me ut, And then t over 2 times at is going to give me at squared over 2, which is exactly what I need to find. Moving on to 7, part B. A small object is projected vertically upwards. Okay, so there's my horizontal ground. This thing is projected upwards. Its initial speed is 29.4. I've got an acceleration downwards of 9.8 meters per second Dotty 1, find the time taken for it to return to its point of projection. So we know s is 0, u is 29.4, which for those who are switched on and have done loads of mechanics questions, you'll know that a lot of the time they can be written in terms of g. 29.4 is 3g. A is minus g, and we want to find the time. Now it's not weird that the equation we're using is the one we just proved, so we're going to use s equals ut plus at squared over 2, so 0 equals 3g times t minus g over 2t squared. And the reason I bring up the fact that both of these can be written as multiples of g is now the g's cancel. Okay, and if I want to go even further and double everything to get rid of that fraction, I can say that 6t minus t squared equals 0, t 6 minus t equals 0, so no need for a calculator even. So this tells us that either t is 0, which represents the instant the particle was thrown, so we don't need to consider it, or t equals 6 seconds. Okay, and then dotty 2, the go-to answer 99% of the time is the object was modelled as a particle. Don't know why it does that, and I can't undo it. There we go, managed to get it back. The other ones you can use are that, I mean, technically the higher up you get, the less the acceleration due to gravity. We're modelling it here as being constant. A consequence of it being modelled as a particle is that all frictional forces are ignored. No spin on the particle, nothing like that. But this to me is your go-to answer. The object is modelled as a particle. So if I underline my answer, and we will move on. Okay, so we've got a pulleys question going on here. Now, I know there's a temptation sometimes for some people to try and do this the quick way with Newton's method, and you can get the answer really, really quickly. Well done you. It's really important you show you're working out for these. I've seen so many students get 1 out of 6, 1 out of 7, 1 out of 8, because they made a simple slip, and because you're showing next to no work, just please believe me, do it the long way. Okay, you may take a little bit more time doing it, but you will save yourself, or you'll gain yourself plenty of marks. So let's turn this diagram into a force diagram. So I've got 2g newtons down there, I've got 5g newtons down here. Remember, I've got tension acting up in each of the cables from the box's point of view. I like to draw a little dotted line, and then I'm only considering what's going on with the pulley. Now, I don't think, and we tend to not really consider ourselves with what's going on above the line, but I do like to include it just in case. And then a little bit of common sense comes in. If you were to let go of this system, okay, you're holding it there in equilibrium. If you were to let go of it, what would happen? Well, B and C would drop. Okay, so they would move downwards with an initial acceleration of A, and this one therefore would move up with an acceleration of A. Oh, I've just looked ahead to dotty 2. We are going to need to consider what's above the dotted lines. So that's good. So if we look at all that, yeah, we've got our diagram all labelled up. Find the magnitude of the acceleration and the tension in the string. So this is a very, very standard question now. So I'm going to apply Newton's second law to particle A, and I'm going to take the direction of acceleration as positive. So that means I've got t minus 2g equals 2a. No more I can do with that. Newton's second law on B and C, and I'm going to take down as positive to be consistent with what I just did. And so now I've got 5g minus t equals 5a. And those two equations make me happy because they look exactly how I was taught they were supposed to look. One is t plus, one is t minus, and the other one is minus t. So I know when I add them both together, my t's will cancel out. Left hand side, when I add them together, will give me 3g. Right hand side will give me 7a. So a is 3g over 7, and because g divided by 7 is 1.4. Okay, that's another nice one to learn about. 7 goes into g, I think 1.4 times. That means this is 4.2 meters per second. You'll see in a lot of these questions, when you have g, 7 or 0.7 or something like that will pop in to make the numbers come out really nicely. So once I've found A, I can then find T by subbing it back into number 1 or into number 2. I'm going to do it into number 1. And if I add the 2g to both sides, that means I've got 2 lots of A plus G, so 2 lots of 14, which is 28 newtons. Okay, so the numbers in this question are so nice you don't even need a calculator. Okay, then if you go back to your picture, you'll notice, we'll go back to my picture, you'll notice that the forces acting on the pulley are tension on one side and tension on the other side. So the total tension being experienced by the pulley is 2 lots of T, which is 56 newtons. And that's it. Okay, looking at the fact there's only 1 mark, it was always going to be something that we could just write down. Okay, nice straightforward 7 marks there, and let's move on. Okay, so that system was left to do its thing for a while, and then somebody pushes a button and C drops off the bottom. Okay, so C and B detach from each other. And what's important then is to note that the weight on one side, the 2g newtons, and the weight on the other side, also 2g newtons, are the same. Now, when there's weights that are equal on both sides, that means this object is then going to stop accelerating. Notice that that is not the same as stopping moving. They will just stop accelerating. So you can see here it says without any further calculations, which means there's no working out for us to be able to do. We can straight away say that acceleration of particle A is equal to 0 meters per second. If you wanted to go into further detail, you could say because the weight of A and the weight of B are the same, therefore there's a 0 resultant force. That's fine, but I would just write this down. Okay, moving on. Okay, we've got a mathematical toy car going on here. Important for us to realise what it is we're given. We're given the velocity here as a function of time, and it's only valid between 0 and 5, so as soon as it goes outside of that, our model breaks down. When t is 1, the car passes point A. Right, find the expression for the displacement of the car from A at time t seconds. Okay, so we're going to start off by integrating. Now it's up to you what notation you use for position or displacement. I'm just going to use x, and we know that we get that by integrating v with respect to t, which in this case is the integral of 50t minus t cubed with respect to t. So that's going to be 25 t squared minus t to the 4 over 2 plus some kind of constant of integration, and I'm going to call that C1, just in case I need to do some integrating later. I can use C2. We know that if we take A as, well, we're talking relative to A, aren't we? So we know when t equals 1, x equals 0, therefore 0 equals 25 times 1 times 1 is 25, minus 1/2 plus C1. So C1 is equal to minus 24.5, so minus 49 over 2. Therefore, x, that's a terrible therefore, but that's better. Therefore, x equals 25 t squared minus t to the 4 over 2 minus 49 over 2, or 24.5 if you prefer. There's really no difference. I mean, there's literally no difference. There we go. Okay, nice 3 marks for us there. Moving on. Okay, when t is 4, the car passes point B, determine the length of the track between them. So given that that expression we just found gave us a displacement from A, we could just put t equals 4 into what we had before. Or, I suppose what you could do is you could integrate the velocity between 1 and 4, because at 1 it's at A, when t is 4 it's at B, so you could find the displacement between those 2 points. I think it's easier to just put t equals 4 into what we had before, so x when t equals 4 is equal to 25 times, and it was 4 squared, wasn't it? Minus 1/2 of 4 to the power 4 minus 49 over 2. I suppose we could do that in our head, but y, let's just put it into our calculator. So I think it's 247.5 meters, and that is it. That's all there is to it. Okay, we're evaluating the displacement when t equals 4. Okay, now if it wanted the displacement from the point where the car started, that would be a bit different, but it doesn't, so it's not. Okay, moving on. Okay, so here, by the looks of it, we've got a pretty standard lift question. What's non-standard is the fact there's a velocity time graph with it. Okay, so the first thing I would do here, if I can move my page, there we go, is try and work out some of the accelerations and the decelerations. So during the accelerating phase, what happens is it increases by a velocity of 5 in 4 seconds, meaning the acceleration is 1.25. Then we've got an acceleration of 0, and then I don't know for the end. Okay, and then I'm going to also draw my force diagram over here. So I've got some kind of tension in this cable, the mass of the lift and the man in it is 500 G. Okay, and then we've got variable acceleration, so I won't add that on. Then if I just focus on the man, he's got a weight of 80 G, and he's got some kind of normal reaction from the floor of the lift, which hopefully you can see there in blue. Find the tension in the cable while the lift is accelerating. So as we just worked out, A is 1.25. Now there will be some marks you can gain for that, because there's only a 4-mark question. I'm guessing there's only 1 mark, but now we can apply Newton's second law to the lift, and up is our positive direction. So I can then say T minus the whole weight in red is equal to the whole mass times 1.25. Now again, you could work that in your head if you wanted to. It's 500 times 9.8 plus 1.25, which is 11.5. So what's that, 555? 5,525, yeah, 5,525 newtons. Lovely. That's a lot of working out space for a short question. Okay, we'll move on to part B on the next page. Okay, part B. While the lift is decelerating, the magnitude of the reaction on the floor of the floor on the person is 704. Right. Okay, so if we think back to our little picture, we've got our guy standing on the floor. We know his weight was 80 g, and we've now been told that the reaction force is 704 newtons. Okay, that's enough information to be able to find the acceleration, and once we know the acceleration, we can use that backwards then to find the time. So Newton second law down as positive, so 80 g minus 704 is equal to 80 A. A must be equal to 9.8 times 80 minus 704. I think that's 80. Yeah, that's 80. And then I divide it by the mass of 80, so I get the deceleration as 1 meter per second. And it's come out as positive, but don't get confused by that. It's positive because I've taken down as positive. Now, if there's an acceleration of 1 meter per second, then if we go back and look at our graph on the last page, I'll pause while you do that, okay, you should see that the particle has decelerated by 5 meters per second over the course of 5 seconds, it'll end up being. So I can say that 1 equals the change in velocity, which is 5 minus 0, over the change in time, which is that. Okay, if I rearrange then, multiply both sides by t minus 10, so I get t minus 10 equals 5, t equals 15 as required. Okay, and so all I've done there is I've said A is change in velocity over change in time. Okay, and I've got all of those bits of information from the graph on the previous page. Okay, moving on to what is probably the final part of this question. And in fact, the final part of this whole paper. Calculate the distance travelled by the lift during the entire 15-second journey. Now what I'm going to do is I'm going to get a copy of the graph from a couple of pages ago. And voila, like magic, there it is, slightly off the page. There we go. So we've got 3 phases of motion here: the acceleration, the constant speed, and then, or constant velocity, and then the deceleration. So we've got this area here, we've got this area here, and this area here to work out the sizes of. So the first one, so distance. Okay, and notice from the graph there's nothing below the time axis, so there's no negative velocities for us to deal with, so it's really quite straightforward. So the area of the triangle is base times height divided by 2, so base times height divided by 2. The area of a rectangle or a square is the product of the 2 perpendicular distances, so 4 to 10 is 6, and then 0 to 5 is 5. And then finally, 10 to 15 is the base, 0 to 5 is the height, divided by 2. So I got 20 divided by 2, which is 10, plus 30, plus 12.5, which I believe is 52.5 meters. Lovely. It is a trapezium also, so you could do the sum of the parallel sides divided by 2 multiplied by the distance between them. So you would do 15 times 6 divided by 2 times 5, that would get the same answer. I think that is the end of this paper. So thank you very much for watching. Hope it was helpful.